Great. All right. So it is my pleasure to introduce today, let's see what you mean by back and front. My pleasure to introduce today our speaker in our computer science seminar, Brian Plancher. Brian is a PhD candidate studying robotics at Harvard, and his research focuses on developing and implementing open source algorithms for planning and control for robotics. By really exploiting both the mathematical structures of the algorithms and doing that kind of algorithms work, and the design of the computational platforms, taking advantage of things and features in things like CPUs, GPUs, FPGAs. And so his research really sits at the intersection of robotics, computer architecture, and numerical optimization. He's also done a lot of really interesting work in STEM education with co-chairing a group called TinyML@Edu. I think I will leave the intro there, and he will be talking to us today about his work on hardware acceleration for real-time robotics. Right.
Thank you. That was way too nice of an introduction. I don't think I deserve that nice of an introduction. Hello to everybody on Zoom. Thanks for coming, people in person. I thought I would just give a little bit of introduction about myself, but some of this was already covered, so I'll skip that part. But
I think you can talk.
Yeah. But hi, I'm Brian. I'm obsessed with my dog Alvin and my daughter Tess, and I'm now realizing this is recorded on Zoom, and my wife told me just to put a picture of the dog and the baby and not her, but I want to say for the record, I like my wife too. She's really great, but I don't have a slide about her here. So as Rebecca was saying, I really like teaching. I love teaching project-based courses in particular. This is one we taught at MIT over the summer, where we did like intro to programming and robotics through a self-driving car race, which was super duper fun and very chaotic. This was the final race, and 16 cars on the track, pure chaos, really fun. But also recently I've been really into accessibility and inclusion on courses. And so we've been really working globally to try to improve access to embedded machine learning education. And that's been this TinyML@Edu thing. So we ran an edX course. We have like an academic network of 20 universities around the world. It's been super fun, and I hope to continue to work on things like this. But today we're supposed to talk about research, so I'll get to the research. As Rebecca said, I do motion planning and control algorithms. And really what I work on is trying to design fundamentally faster, more robust, more reliable algorithms so that they can be used in the real world. Right, today, a lot of robots are sort of confined to the lab, and my hope is that as we develop better algorithms, we can actually get them out in the field, doing disaster response, working with people in the homes, more advanced prosthetics, or as many of you might be running into right now, better logistics because COVID-19 supply chain terrors. And so really what I want to do is get those algorithms out there and make them better. But before we dive into sort of my approach and how we do that, I just wanted to get to know a little bit about everyone that's here today and here on Zoom, so I can make sure to target the talk accordingly, because I know we have a pretty diverse crowd of backgrounds. So I'm wondering, both on the Zoom and in person, let me see if I can make this bigger so I can see all the people on Zoom. How many people are faculty staff have like a degree in computer science, a background? It's a bunch of people, okay. How many of you are like juniors or seniors, taking a bunch of courses sort of far along in CS-ish? Okay, how about like freshmen or sophomores interested in CS? Awesome. How many people have no CS background at all? Cool. So I want this talk to be accessible to all of you, regardless
of reading books.
Okay, who's read a book on CS? All right, awesome. So I want this talk to be accessible to all of you, and so if you have questions, please just stop me and just interrupt. Just feel free to interrupt as we go through. If you want more detail and you think that I'm not giving you enough detail because you have a background in this, feel free to stop me. For people on the Zoom, feel free to just jump in and unmute yourself. It's sometimes hard to see all the raised hands here while also looking at the slides, so feel free to just jump in if that works for you. Or maybe if Rebecca's on the Zoom and she notices, feel free to just interrupt me as well. So with that, let's actually talk about some robotics. This is Boston Dynamics Atlas. This is a recent video from about, I think, 3 months ago, and hopefully it streams okay. But basically what I wanted to start here was that robots can actually do pretty amazing things. For those of you that haven't seen this, I'm just going to let this play because I think it's really awesome, and Atlas can actually do things that I personally cannot do dynamically, which is pretty impressive. And so this is sort of the motivation and the excitement here, is that if we can get these robots out in the real world doing these amazing things, couldn't they actually help people, right? Could we actually get them in the home and doing all these sorts of things? But I'll pause for a second and just let you watch the end of this because it's awesome.
Really cool was a dog.
They have.
They have one of those too. This is the part that I couldn't do.
Whoa.
You know, synchronized double backflips. Not too bad. There you go. And so this is sort of in the lab, we're doing these amazing things, but the problem is there's still a long way to go to get them actually working in the real world. So thankfully, which helps me in my talk, Boston Dynamics released a behind the scenes video. And what you can see in the behind the scenes video is, you know, to get that one video required a lot of efforts, a lot of trial and error. There's a lot of failures. After this guy talks for a second, we'll see more crashing, you know. And so these robots are awesome. They can do amazing things, but not all the time. And you really wouldn't want that kind of fall happening, you know, in your living room, you know, when you left your dog left the tennis ball, now the robots will come in and just totally took out your dining room table, you know. And so in order to get these robots into the real world, we need to make them better. We need to make them more dynamic. We need to make them react to the real world in better ways. And so how can we fix this? There's actually a lot of ways we could think about fixing this, but two ways that I like to approach it with is try to make the robots smarter and think faster. And that's through better algorithm design and through hardware acceleration, which we'll talk a lot more about as this talk goes on. But before I dive into the actual content, I just want to talk about what I hope you take away from today, especially those of you that have less background in computer science. I hope you learned some of the language of robotics and to a lesser extent computer architecture. So therefore, in the future, if you get excited about these things, you can go into a class and feel like you actually sort of know a little bit of the basics, right? Because we don't have a lot of time. I would love to teach you a whole course on this, but we got 30 minutes, so that's what we get. I hope you understand the importance of parallelism in high-performance computing and why I think parallel is the way to go. And I hope to give you a little exploration of what hardware acceleration is, both the process and sort of the opportunities there. So in the whole spirit of asking for feedback, do we have any questions so far? Great. Okay, so I'll give you a little bit of overview of robotics, then architecture, then we'll do that case study, and then we'll talk a little bit about the future. So robotics. Robotics is a really big space, which means both there's a lot of opportunities and there's a lot of things you could possibly cover. We have lots of different kinds of robots. You have self-driving cars, you have drones, you have industrial arms, you've got quadrupeds, bipeds, so there's your dog. That's the MIT cheetah. But all of them sort of operate in the same way, in that they have some amount of sensors on them, whether that's a camera or some sort of force sensor on the foot, or maybe the spinning LiDAR thing on top of the self-driving car, and that sends some data into some amount of computers on the device attached to the device. They take that data and then they figure out some sort of command to send to the actuators, whether that's wheels or rotors or joints or whatnot in the robot to get it to do what you want it to do. And today we'll focus in on that compute. That's where my research is. But I just want to name that there's actually a lot of really exciting research that a lot of people are doing actually on new actuators, new sensors, lots of different kinds of hardware as well. So there's even more to robotics than what we'll talk about today. And hopefully I can give you a little bit of high level on a lot of things going on inside of computation. So the way I like to think about the computation for robotics is that information is coming in off of those sensors, and it's coming in into some middleware operating system type thing that's doing sort of, okay, information in, information out, and it's sending that information down into some amount of core algorithms. And those algorithms are sitting there actually doing the thinking, but they rely on some core computational kernels that run actually on the hardware. And the reason why I want to break out the core computational kernels in the hardware is that often when we're writing software for robotics or just in general, you sort of just do like a, import NumPy or import some sort of thing or pound define, pound include, you just use some libraries and they're good, they're great, they're fantastic on CPUs. But as we'll see, those libraries don't always exist if we're targeting alternate hardware. And so we need to make sure that we have all these things all the way down to actually get the performance that we want. Just to make it a little bit more complicated, but also give you a little more language. The algorithms in robotics are generally split into 4 stages. So as you think about exploring robotics, usually there'll be people that sort of specialize in one or two or maybe three of these sort of stages. And usually what starts with is perception, which is often, but not always, computer vision. It's sort of the raw information comes in and you sort of have to perceive it and get some higher level information off of it. So if it was computer vision, that could be something like turning raw pixels into, oh, that's a car, there's a lane, you know, there's a person, right? And then all that sort of higher level information comes into this mapping and localization block, and there you build some map of the world. And depending on your application, that could actually be at a lot of different granularities. It could be, you know, a 2D grid that says safe, bad, right, for all the different little spots. Or it could be some complex 3D rendering, fully graphical, really beautiful kind of thing. That map and the localization of you in that map is then generally passed to a planning algorithm, which then says, okay, you're here, you want to go there, how do I get from point A to point B? And so you plan some route through the map, and then you use the control block to actually execute that. And the reason why we have to talk about control is that you can imagine if you're some robot walking through the world, well, you might actually think that you can just walk in a certain way, but you go slip on a little bit of ice or something. And so now you actually have to react and readjust and get back on that plan. So that's why you need to think about both planning and control.
So is that computationally feasible physics, or is it remaining a black box with machine learning?
Both. So there are a lot of traditional approaches that will use physics models, and then recently people have actually been applying a lot of reinforcement learning. And learning sometimes only answers one block, and sometimes people are using learning to answer multiple blocks at the same time. So there is recent research in pixel to action. So to get rid of this whole thing, just put a neural network in the middle. There's also a lot of research that says, let me augment some of these different steps. And there's even things that do a little bit of both. So we have a full physics modeling, but then we say, you know, my model isn't perfect. Can I learn some adjustment to my model to make it better? There's actually a really cool paper that I like that took a drone, and they said, we can have a basic model of a drone that works pretty well most of the time. But when we get really close to, say, a table, there's some weird downdraft forces on the rotors that are over the table that I don't know how to model. So can I take the basic model, put a neural network next to it, and then learn those downdraft forces and then get it to fly better? And the answer is yes. Personally, as you'll see, I like physics. I like using some of these basic models. So things I find most exciting are those kind of combination pieces that try to take the best of both worlds. Anybody else with some questions right now? Cool. So I've been lucky enough to get to do work kind of across the stack and across a lot of those algorithms, and also do some CS education papers as well. But the majority of my research and what we'll sort of focus on today lives in the planning control algorithm space and thinking about how to bring that down onto hardware and take advantage of computer hardware to make it fast. And that's working at the intersection of robotics. And as Rebecca said, mainly computer architecture and numerical optimization, but also more recently, trying to bring in machine learning and seeing where can we use machine learning to augment these other approaches and make them better. And today, the example we'll do is pretty squarely in the robotics computer architecture space, focusing on a core computational kernel to try to make this whole hardware acceleration flow a bit more of a reality. But that's a lot. That was a lot. That was a whole course on robotics in 10 minutes. So just pausing and making sure nobody has any other questions right now. Cool. So let's do another whole course in another 5 minutes. Let's do a crash course on architecture. And in particular, we'll focus on the GPU. But in order to get to the GPU, we have to start with the basics. And this was the big takeaway for me from the computer architecture courses I took in graduate school that sort of blew my mind, was that computers aren't really getting faster. So for the students in the room, you might have only lived more towards the end of this, but I started living more in the beginning here, and I sort of grew up with the understanding that computers just got faster here. But it turns out since about 2005, the clock speed on computers has remained roughly the same. We've been kind of stuck in this couple of gigahertz space. And this has some really big implications, because this means that if you have a program that runs, you used to be able to just know that it will be faster next year. So if your algorithm is a little too slow, you just wait, and work on another algorithm that does something cool, and it will get faster. But that's not the case anymore. Instead, what we've had is this growth of parallelism. And this is actually why your computer feels faster. Because now you don't have a single core computer, you have a quad core computer. So when you open 37 tabs of Chrome, along with Excel and PowerPoint and Word, or whatever your favorite applications are, now the different cores can be sharing that computation, right? Or maybe one of them's running PowerPoint, one of them's running Chrome, and therefore your computer feels faster. And in fact, for you, it is faster. It does the things you care about faster. But for that one single program, if we don't take advantage of the fact that there is now parallelism, we're not getting any faster. And that's sort of one of the really big motivating factors of a lot of my work is think about parallelism. We need to make sure that these robotics algorithms are taking advantage of it so we can go as fast as possible. And this is true not only on the CPU, but also moving from the CPU to the GPU, or the graphics processing unit, which actually has even more parallelism. And the sort of the inspiration for a lot of my work in terms of, well, you know, this thing does graphics, like why are we talking about it for robotics, is that starting in the mid-2010s, NVIDIA basically created this ability, and then now it also works on AMD and all these other sorts of GPUs, to run non-graphics programs on GPUs. And the first big win was machine learning. And now actually all this cryptocurrency stuff, which is why GPUs are out of stock, and now it's a whole thing. But essentially, even as early as 2015, you were seeing these like huge boosts in speed up by running neural networks on GPUs. And so this sort of inspires me to say, well, can we do this for other robotics algorithms, right? Can we do this for the planning and control approaches that maybe don't use as much machine learning?
Isn't there a third architecture emerging which is tailored specifically to machine learning?
There are
Apple chips and Google chips.
Yes.
Are those to the planning stage, or would you put those in intro to learn on the job?
There's a bunch of different domain-specific architectures you could make. Most of them are generally designed to just run a neural network, not actually be able to train a neural network. So in general, you have to
backwards, in other words.
Yeah, you'd have to train it ahead of time and then deploy it onto that. But at the end of the talk, I will preview the concept of maybe a robotics special chip. But we're going to get through hopefully we get through the GPU first. And is that good for your question? Anything else? Anybody? Cool. Okay. So in order to sort of understand why this might be the case, let's sort of look at what the difference is between a CPU and a GPU at a super high level. So there are a lot more things going on inside a CPU than just this, but this is my sort of like high level here. Let's see the difference. So, your computer has the quad cores, right? So there's 4 cores here. And each of these cores has some amount of control logic, which is sort of thinking about how to do all the different things that it wants to do, some amount of memory in its cache, and some amount of arithmetic and logic units that actually do the math, right? And on those 4 cores sort of share some memory down here. So we can sort of shove that in there, right? And the difference, if you look at a CPU and a GPU, is a GPU still has that same memory thing, but now we've introduced many more cores, and each of the cores is not as smart, doesn't have as much memory, but has way more capabilities to do math. And so the big difference here is that your GPU is really good at doing structurally easy and regular computations with lots and lots of math. So the best sort of example that's not graphics is matrix multiplication. So if you've taken linear algebra, remember matrix multiplication. If not, basically what the process is for every output cell, if you multiply 2 matrices, you take a row from one matrix, you take a column from the other, and you compute their dot product, which is that you multiply each of the little values and then you add them up. And so you can imagine that actually kind of works pretty well with something that doesn't have a lot of smarts, in that all you tell it is, hey, you take this row, this column, 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 and all of you do the same thing, and just give me the output over there. And so that's the kind of algorithm that works really, really well on the GPU. And it turns out that machine learning is often a lot of these matrix operations, which is why we were getting such speed ups. And those data flow architectures you were talking about, a lot of them are just super duper specialized matrix operations for specific kinds of neural networks to make them even faster.
Either of them get better than the N-cube complexity of the sequential algorithms?
Yeah. So in fact, if I launch this on the GPU, I can do all of the cells at the same time.
No, that's the typical dumb algorithm for matrix multiply is N-cube.
Right, but I can do it.
Strassen. Can you do something like Strassen?
Oh, yeah, you could totally try to think about something like this, but I actually think that So they're highly specialized architectures that do various things in different ways. I would say on a general purpose GPU, you might actually do better just by doing NQ, because since I can do them all in parallel, like I don't need to worry about sharing stuff, but actually they do certain things like they'll pull tiles in the matrix to make sure it fits on the GPU and then do, yeah. So there's lots of different little tricks you can do, but in general, when the GPU is good is when we can just go parallel. So computer architecture in another, 5 minutes, how are we doing? Everybody still with me? Okay. It's still with me, great, saw a thumbs up there. Now that we know a little bit about robotics and a little bit about architecture, and hopefully now you can take that back to whatever you want to do with your careers. Let's talk about accelerating rigid body dynamics. And so we'll do that again in 3 steps because, why have 1 step? So first of all, you might be asking, why should I care about this algorithm and why should I accelerate it? Then we'll actually do it. And then we'll talk about what you were saying from before. How do we move beyond the GPU? So rigid body dynamics is one of those core computational kernels that I care a lot about. It appears in a lot of different algorithms across the robotics stack. And so it's one of these things that gets imported and called a lot. In fact, for a case of algorithms called model predictive control or nonlinear model predictive control, which I personally care a lot about because I do algorithmic work on these, the gradient of rigid body dynamics actually often accounts for about 30 to 90% of the total computation time, depending on what paper you're citing and what exact example and their exact implementation. So it's a very time-consuming kernel, and it's a very important kernel, so it's one that we might want to consider accelerating. And the reason why I'm excited about thinking about it on the GPU is that in a lot of those algorithms, often what happens is you have a robot that's moving and making a plan through time, so it's this robot arm, and you have some start state, you have some goal state, and you probably also have a bunch of waypoints along the way, and you're trying to basically plan this path of waypoints. And so what you're going to want to do is compute rigid body dynamics at each of these waypoints. And this is very expensive, right? As you increase the waypoints on the CPU, the time just goes up, 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 up. But often in these algorithms, you want to compute them all as like one step in the algorithm. So each of these computations is naturally parallel. We could compute them simultaneously if we had the hardware to do it. And so this begs the question, hey, if I have this really parallel GPU hardware, could I go and compute these all at the same time? So that's why we might want to use rigid body dynamics. So how would we actually go about doing it? And what we have to remember is that the CPU and GPU are different, right? The computational patterns are different. And so we need to do this process called hardware-software co-design, which is just a fancy way of saying we need to specialize our algorithm for this hardware. We need to think about how to design it so that it works well on the GPU versus works well on the CPU. And so we need to think about what are the features of our algorithm and how can we sort of specialize it. So the first one was this parallelism thing, which good on the GPU, bad on the CPU. Great. I might want to use the GPU. The question is, what else is going on in rigid body dynamics? And does it map well to the CPU, to the GPU, and how might we want to adjust it to make it better for the GPU? So what is rigid body dynamics? Well, it's basically just physics. It's robot physics. And the reason it's rigid body is most of our robots are metal, and they sort of have these rigid links and joints. And so you can think of them as sort of a bunch of blobs with a bunch of joints connecting them. And this is a rigid body approximation of robots. Now, there are soft robots, there's a lot of other kinds of robots, but a lot of the main robots that you'll see operating in the world right now are these rigid body things, so we can use this rigid body physics. And in terms of dynamics, dynamics is the part of physics where we do F equals ma. It's the study of forces and motions on bodies. So we're looking at forces and acceleration. So we're trying to compute things like, if I put this much torque into each of the motors along my robot arm, like where does the end effector end up? How fast is it moving? What's its acceleration? Or conversely, if I want it to move here, what kind of forces do I need to put into the robot arm to get it to go there? And how do these algorithms work, right? We care about the features of the algorithms, not just the algorithms itself. So I'm going to stay super high level because, again, developing these dynamics algorithms, we could do a whole course on it, which would be really cool. And if you want to, we'll talk about it more later. But basically, the way these algorithms work, RNA being a particular one, is there's some sort of looping up and down the tree. And so this is because you see these links here, right? So for I equals 1 to n or n to 1, the links are usually numbered in order. And so what this is basically saying is we're going to go out the tree and then we're going to come back down again. And what we're going to do as we go out and down is we're going to collect some forces, velocities, accelerations as we go. And you can think of this as, imagine you're moving your arm. If you move your shoulder, that has some result on how much your hand moves. And so you have to kind of understand how all the joints are moving to understand sort of where the tip is moving. Then if you put a force on the tip, that force kind of works its way back down the arm. And the way it works is through kind of a mess. But the big takeaway here is there's a lot of different things going on. We have actually a pretty heterogeneous computation here. There's additions, there's multiplications, there's cross products, there's a lot of different stuff going on inside of each of these things. And it generally has to do with inertias, masses, transformations between the joints. But what's important for us in terms of characterizing this algorithm is that there's kind of a lot of different stuff. Right, so we're trying to compute some forces and motions, and we're doing it in this loopy manner with a lot of different operations. And so,
are the servos susceptible to momentum, or are they just do position?
Depends on the robot. Some of them are servos, some of them are not. Some of them are just like torque controlled motors.
Like us.
Yeah. So they can have stiction, they can have inertia, they can have lots of different things, which again makes this modeling kind of complicated because you have all these various terms in here, but it's trying to capture some of that. And just one quick note before I say why that all matters is technically I've been talking about the gradient of rigid body dynamics, and I just wanted to note that like it's the same algorithm. We just are taking a derivative, so there's just like a bunch of DUs everywhere. But if you look at the algorithm, it was like 2 loops DAF, and now we have 2 loops DB DADF. There's just more work to be done, which is actually good for the GPU. But the point I want to say is, so the algorithmic features we have is these serial dependencies on these loops, and we have lots of all these different operations going on inside of that algorithm, which is totally fine on the CPU. The CPU is like, great, I'm a general purpose machine. You give me these different things to do. I do it. You have lots of serial dependencies. I don't really care. I have a big cache. I'll store it all in memory, and I'll refer to it as we go. On the GPU, this is really bad because the GPU, remember, wants this big regular matrix multiplication, and it wants to do it all at once. And so if you tell it, no, do this one thing, then this next thing, this next thing, and by the way, it's always changing, that's not good. So the real trick here is saying, okay, what can I do to fix this algorithm to make it actually run better on the GPU? And so the first thing you can do is we can try to move as much as possible, and don't worry about all the math, but the takeaway is move everything into parallel loops that we can, right? And so basically, instead of doing this whole big blob, well, maybe these things are fixed, so I can pull those out and do them ahead of time. And then in the serial loop, I can do as little as possible. So I can do a big parallel step, I can sync, and then I can do a little serial step. So that's the first thing you can do. The second thing you can do is you can reorder the computations so that they're unified. So I can do matrix multiplication, cross products, matrix vector math, more cross products, right? I can try to do these various coalesced steps, all one thing at a time. So now we're actually fitting the programming model of the GPU better, right? We're doing one step at a time. We're doing it in parallel. And then when we have to do these serial things, but we're trying to minimize those as much as possible. Good? Okay. And then there's one other thing we can do, which is that we can actually look at the robot itself. And if we have just this one robot arm, we have to go out the links and back the links. But if our robot has some branching, we can think about the fact that actually as it starts to branch, we can consider each of the branches in parallel as well. Because if we're only going out and back, this refers to these two, but then once we get to 5 and 1, now as we keep going down, the next level is completely independent. And so we can start to actually branch and do some in parallel stuff, even within the serial loops.
So EV mounts have cycles. Can you handle cycles?
Yes, with some slight changes to the algorithm. Often cycles are handled through some additional constraints that you can put on the problem, or you can do a slight variation on this. The exact algorithm shown here would not handle cycles. But fortunately, most robots don't have cycles. So usually we're okay. But that's not, but like we had a robot that did, because it had a sort of a pull that went from its ankle back up to its hip to kind of like keep it in line. And so that actually added some complexity into this. But basically, we do all that refactoring. And what happens is we get a huge speed up. So this was sort of a naive baseline GPU implementation of that algorithm. it was taking, I don't know, 55 microseconds. And then we refactor it and we're 6.5 times faster, 6.4 times faster. And suddenly we're only here. And this is for like the worst possible robot to try to prove my refactoring is working on. It's the robot arm. I have no branching, so I can't take advantage of that. But even just moving the values around and doing this parallel step, then doing the serial step, we get this huge speed up. Now, what I do want to note, how we don't have time, is that the CPU is still faster for one computation. Because this is a very serial computation, this computation actually doesn't fit super well on a GPU. So you might now be sitting here and saying, Brian, why did you put me through 30 minutes talking about this? It's slower, this doesn't work. Well, the point is we don't want to just use it for one computation. I'm using the one computation to show you how powerful refactoring is. What I actually care about is what happens when I have many computations and what happens when I have more and more complex robots. How does this actually scale? And is this now where the GPU can have some benefit? Oh, it looks like there's something in the chat. Can you please repeat questions asked in the room? Ah, yes, I will repeat questions asked in the room moving forward. Sorry. So let's go back to this now. Now I'm clicked off the PowerPoint. Yes. Okay. So let's go back to this plot, right, where we saw the CPUs getting slower and slower and slower, and this was the computation that we actually care about. Well, now we put it on the GPU. Now things are looking good, right? The computation basically scales for free. There's some amount of time to compute 16 of them, but once we do that, because we can just do kind of as many as we want in parallel, it's the same amount of time for 16 as for 32 as for 64. It's like literally exactly the same. When we go to 128 and 256, that's just a little bit more. We kind of like just went beyond how many I could fit on the GPU at once, and there's a little bit of serialness going on, but basically the computation scales for free. But I want to point out there's also these gray bars here that we need to think about, which is that if we're just moving this one step of the algorithm onto the GPU, we need to actually send information to the GPU and back again. And so we now have this additional I/O overhead. And so what we get is sort of speed ups that get better and better as we get to more computations. But we do have this I/O penalty that's kind of cutting our speed up in half. But it's pretty interesting to me because I'm running this on an 8-core CPU. It's a brand new 8-core CPU. It's a pretty good CPU. And still, for only 16, I was like almost just as fast, including I/O on the GPU. And I can beat it by a lot as I start to go to more computations. So that was pretty exciting. And then if we move to, say, a branching robot, what happens there? Well, two things happen. One, the CPU gets even slower, because now we have more work to do. We have 12 joints in here actually now instead of 7 over there. The GPU actually got faster. To compute more, it did it better because we now have branching in our robot. It's imperceptibly faster on the graph because it is basically the same time, but it's like slightly faster in terms of the computation per each one. And then the scaling continues to be really fantastic, and the GPU is way better. But now I/O becomes even more of a problem because there's more data to send back and forth because we have a bigger robot, more values that we actually care about. And this sort of scaling continues if we move to the humanoid. This is a new scale because it's much bigger, much more complex. But again, we have the same sort of thing, although I do point out that the GPU is not a panacea. At 128, 256, we do start to get a slowdown there because this requires so much memory per computation that we're actually starting to fill the GPU I have. So the takeaway I want you to have from all of this very busy chart is just that computations scale much better on the GPU, right? If we can find a computation inside of some robotics algorithm that has a lot of parallelism, that has a lot of scaling that we can take advantage of, we can get some really nice speed ups, right? We can get almost an order of magnitude speed up. But I/O overhead is a very serious concern. And so this is why, personally, I would like to move the whole algorithm onto the GPU. So I can just send a little bit in the beginning and a little bit in the end. Then I can remove this whole I/O overhead, and then I get my 7.6x instead of really 3x speed ups, including the I/O.
Would compressing the I/O overhead be a reasonable direction for research? I mean, our nervous system doesn't seem to be that high bandwidth.
Yeah.
Our brain is, but not our nervous system.
So the question is, could we compress the I/O because the human body doesn't seem to be that high bandwidth? And the answer is maybe. I think there's also a lot of ways to think about distributed intelligence instead of just a centralized intelligence to deal with the really high frequency things, and then to have a lower bandwidth thing working, in the central area, and then the IO becomes less important because you're actually running that at a slower rate.
The octopus model.
Yes, sort of the octopus model, as was said in the room. But even still today, these centralized algorithms can't run fast enough. And if I start to add in things like now consider robustness. So now don't just track the state, track a distribution over the state to make sure it's not, now it suddenly exponentially blows up in size. Or now deal with contact. Now I have actually this discrete variable of contact, so you get an exponential blow up. So there's a lot of room for just computational things. Now to pause, yeah.
Just there's a question in the chat, which I can either read to you or you can read as you prefer.
How does the solution of using parallelism in the GPU influence the robot's appearance/configuration? What is the trade-off between having more branching and, say, a stronger trunk? That is a great question. I'm not a hardware expert, so I don't have like the full answer for you, but I can tell you that a quadruped is a great option for computational efficiency in terms of physics, because usually you have one solid core and 4 limbs that have a couple of links on them. That's great. That's my favorite one. It's very easy to compute. It's also very easy to actually approximate as just being one blob of mass with some like rockets on its legs, and that kind of comes up with a decent approximation. So this is also why you see actually quadrupeds out in the wild today, and you don't see the humanoids, because it's much harder to actually approximate that and model it and handle it. I think there's some really interesting work, and there's some recent new papers on co-optimizing algorithms and hardware. But that is super challenging because you end up with a lot of nonlinearities, because like the algorithm impacts the hardware, which impacts the algorithm, which impacts the hardware, which if you change it too much, then it can't walk anymore. But if you change it too little, then you're not. So there's all these sorts of coupling problems there. And so I think it's actually a really interesting research direction. My personal bias on all of this is that probably the most useful general purpose robot is something that has wheels that can lock, and then it can walk upstairs. Because wheels are just so efficient. So why are we trying to walk everywhere if we could drive? Like, this is why we invent scooters and bicycles and things like that. So I really liked, Boston Dynamics had a robot called Handle that they were playing around with for a while, which basically had 2 big wheels on the bottom. And it would kind of just drive around the warehouse, and then it could block them and then move its legs and sort of step over something if it needed to. That to me seems like a really cool platform. But again, I think that's a really open question. And actually, it's sort of the answer to most things in robotics is we don't know, which is why robotics is really exciting, but also why robotics is sometimes terrifying, because it's like, there's so many things we can do better. But that's why I think it's a fun place to do some research. Yeah.
How might moving to more GPUs than CPUs affect the cost of building a robot?
That's a really good question. Okay, so the question was, how might moving to more GPUs than CPUs affect the cost of a robot? Right now, with the supply chain shortages that we have, it would be prohibitively expensive because basically all the GPUs have been bought up by the Bitcoin miners. But in theory, if GPUs start to be produced in more mass quantities, they should be relatively cost efficient with a CPU. It's kind of just going to be a supply chain economics thing. Although it does introduce different power and connector and sort of layout requirements on the circuit board. So NVIDIA has actually produced a bunch of these things that they call Jetsons, which is basically an embedded GPU CPU package that you can just get one of. And so they've sort of solved the problem of like putting them next to each other, having the memory be really fast, and they sort of give you a GPU and a CPU, and they have pretty low power requirements, and they're relatively cheap. They make one that's like $100 or less. So it's possible that this won't actually have a big impact in the future. Right now, really hard to get a GPU today, but hopefully that's a COVID supply chain issue and not a long-term issue. Anything else?
Well, this might be, so robots, like we've seen Asimov, like we've had Asimov like a very long time ago, and now we have Boston Dynamics, but it seems that the movement is still very unnatural. Is it because like the natural human sort of walking motion is like the physics of that is very costly to compute? Is it because we're actually walking inefficiently? What do you know is the reason behind that?
So there's a question about the biomechanics of robots, basically, in that we've had Asimov, we now have Atlas, and they walk like robots. Why don't they walk like humans? So There's actually been a ton of studies in the literature about the biomechanics of walking, and humans are actually really good at it. We're very energy efficient. Part of the problem historically has been that we can't compute the full physics model of a very complex biped in real time, full stop. So therefore, a bunch of approximations are generally made, and those approximations are made to make it more robust and more reliable, but they make it walk like a robot. So for example, you'll see most robots will actually drop their hips pretty low to the ground. This means my center of mass is now much lower. And so because my center of mass is lower, I am more balanced, right? There's less distance to fall from. And then robots will probably take lots of really fast steps. Because if my feet aren't that far off the ground and I misstep, well, it's gonna hit the ground really soon. So there's less like falling potential, there's less direction fall. So all these things are approximations people have made to try to get around the fact that we actually aren't computing really good things. And so that's why for a lot of my research is, well, how do we actually compute really good things so we can actually get it to. If you look at some of the simulation results from some of these nonlinear model predictive control approaches, you get very human-like walking. There's some good ones that came out of the DARPA Robotics Challenge of Atlas, the original version. And so the MIT team will show, they didn't run it because they were too afraid that it would fall in real time, but like they showed it in simulation, and Atlas essentially at that point was wearing like a 200-pound backpack because it had like all the batteries and stuff behind it. And so it basically ran like somebody who was carrying a really heavy backpack, you know, it was like kind of hunched over a little bit and it was like running along. And you're like, oh, okay, like that makes sense. But of course, we need to do that in simulation with time slowed way down, which is why I think this hardware acceleration stuff is particularly important.
So it's a matter of like we still haven't had the computing power and the efficiency required for these computations.
Yeah, we don't have the questions about computing power and efficiency, we're not having it, and we have it, just not in something that we can put on a robot. Or we have it, but I need to make certain approximations to get it to run fast enough the robot doesn't fall before I compute it. So yeah, the computing power. It's not necessarily the compute, it might be more the algorithm, it's both the algorithm and the computing power, which is why my research is both in algorithms and hardware acceleration, but they're both problems, yeah.
When we have soft flash, shouldn't the optima be in different positions anyways?
The question was, we have soft flash, shouldn't the optimum be in different positions anyway? Yes. I think we're actually seeing robots move more towards having some softness and some forgiveness. I still think we're going to run into computational issues, even if the robot's foot is no longer a metal plate, but it's something that's a little bit more flexible. We're still going to have problems. So like actually a lot of robots, you'll now have a little rubber thing on the bottom of their foot. That is to give a little bit of give. Right, because we know that we're not going to perfectly compute the touchdown of the foot. And so we want to have a little bit of room for error, so cover. But we still have to actually compute all the physics. Or run a neural network that computes all the physics. Good for now? Good on the chat? Cool. Okay. So to answer the question from earlier, which is, can we do better than a GPU and do a custom chip? Yes, we could. So, oh no, I clicked the chat, so now I lost the click. There we go. And so there's an example of this thing called, if we go back to machine learning again, the tensor processing unit. It's this thing that Google made, and they actually have it deployed in their data centers. If you go and use Google Colab to do some research, you can actually use a TPU in real time. And basically, don't worry about the actual data or the scale, but the TPU can actually outperform the GPU, which outperforms the CPU on some specific neural network tasks. This is particularly like a power efficiency one for the Google data center use case, but in general, when you go to some custom hardware, you can actually get this speed up. So that naturally begs the question that was asked earlier, which is, okay, GPU, CPU, what about custom chip for robotics? So I'm going to take this graph, I'm going to move it over to the left so I can zoom in a little bit, because that baseline was way too slow. And basically, we did some work to try to synthesize a custom chip for the robot arm doing its dynamics. And it's really, really, really fast. Like really fast. Because if we do a fully custom chip, we don't have any of the GPU problems, but we can get all the GPU parallelism. So we can actually still compute all these things in parallel, but now we can actually have a specific circuit that does just this computation, doesn't worry about being regular. I can actually take all those computations that I had to move to not do them at the same time, do them all at the same time, you know, and then I can just fly through this computation. And remember, this is the worst possible robot to be doing this example on. So if I used a more complex robot, we'd probably have an even better speed up. But the one thing to keep in mind is developing custom chips is really time consuming and really challenging. And so to me, the GPU is kind of a sweet spot where we can get some of this acceleration and we can start to characterize the algorithms and start to explore parallelism and get speedups without having to spend a significant amount of time developing these custom chips. And it's more flexible. So since the robotics algorithms haven't fully landed on the one exact answer yet, we can actually adjust our solutions relatively quickly and be actually more flexible for deployment today. That said, I do think that in the long run, we do want to look towards building these specific chips. And we want to look at what kind of kernels do we know are definitely going to be there in the future. I believe that physics will be there in the future. So that's why I'm excited to do work developing, robotics physics chips. And we're working towards some automated design flows on the FPGA and on ASICs that can do sort of what I was showing you before on the GPU with many different robots, many different ones. And I think that'll be really useful. And I'd love to build on top of that and then think about how do we target all these different platforms. So that was a quick case study in accelerating rigid body dynamics. I hope from that you appreciate and understand that hyperacceleration is really cool. It can be really powerful, but there are some real challenges about thinking about how you map an algorithm to hardware. And so I just wanted to end with a little bit about the future of accelerating robotics, or where I think and where I'd like to go. And then I just want to open it up to general questions about anything. And I have some more slides if we want to talk about specific things. Maybe I have the right slide. So the first thing I want to point out is that, as I sort of mentioned in passing earlier, most roboticists, or not most, but a lot of roboticists work at the application level. And they say, okay, here's this toolbox like Drake that does a bunch of these algorithms for me. I'm going to think about what's my use case, what's my robot, and I'm going to use this toolbox to do things. The problem is most of these toolboxes only target the CPU, or at least they only target the CPU for most things. And so one of the big pushes of my research and where I'd like to go is thinking about how do we actually develop a toolbox that can actually target GPUs, FPGAs, ASICs, all these sorts of things. How can we actually let any roboticist come over and say, hey, I want to use this. I want this accelerated. How can I use this? And so the recent work that we've been doing on rigid body dynamics, we actually released an open source thing here. You can go to the GitHub and play with it, and you can take any robot model in the standard URDF format, which is like the standard robot model format, and it'll spit out optimized GPU code for the dynamics. And so what I'd like to do on that is continue this work, do more of these core computational kernels, because there's a lot of them. You can think about, maybe collision detection, good to not run into things, probably a useful, kernel to figure out for robots, but also build those algorithms on top of that. And that's going back to a lot of that nonlinear optimization and other sorts of things. And build some sort of toolbox where roboticists can just come in and say, just like they could with something like Drake, okay, here's my robot, please optimize a path, go. And it will just do it and run it on the GPU for them. So that's one big thing I would like to do. And I think this is actually a lot of fun and something that you all back, if you wanted to, could get involved in, because I think there's a lot of work to say, I want to look at this particular algorithm on this particular piece of hardware. How can we explore what we can do there? Or even how do we characterize this set of algorithms to understand what are the kernels that we need to accelerate? So there's lots of different entry points, and I think there's lots of ways to break this up and do this in small projects, which would be, I think, a lot of fun. And I think it's pretty impactful, because if we can deliver this toolbox, then everyone can use it. And then everybody's robots just get better. So that's one big thing that I'm interested in. The other one is I haven't mentioned any of the machine learning, so I thought I would mention, one machine learning type project that I'm particularly excited about, and I think could be particularly fun. And that's working with little tiny robots. So we've recently released a bunch of these little cute robots that are pretty awesome and pretty low cost. And they can actually do pretty awesome things.
Can I try one?
Yeah, these things are like 250 bucks. It's called the Biddle, and you can buy it online.
Biddle.
Yeah. Now, it's got limitations, right? It's got only 4 joints, so it can't actually move its shoulders. It can kind of just plod forward. And if you want it to turn, you kind of have to like shuffle a little bit. But it gives some unique opportunities for robots to go into places they haven't gone before. You can imagine actually, well, one, it could just be fun to use in a classroom, and it's pretty hard to break, so that's nice. But 2, you can imagine in like disaster response, it might actually be really nice to have this, crawling through little areas to try to like find people. And there's this new technology called tiny machine learning, which I sort of mentioned in the beginning with some of the teaching that we've been doing. And it works to take large machine learning models and compress them down onto small little microcontrollers that we can put on top of these robots. And so I think there's actually some really interesting possible work that can be done about saying, how do we actually take all this machine learning and robotics, and instead of using the world's largest GPU or custom chip or whatnot, how can we compress it onto one of these little tiny microcontrollers and actually deploy it onto these robots? I think there's also a non-machine learning side here, which is, how can I also take some of these traditional approaches and run it on these small robots as well? Because when you introduce the microcontroller, we now have a whole new set of constraints and a whole new set of opportunities to do cool things. So that's one other little project I'm particularly interested and happy to talk about more. So before I end, I just want to make sure to thank all of you for being here today. Thank you for taking the time. I'd like to thank my funders, mainly NSF, and I'd like to thank all of my many collaborators, because working across multiple disciplines means that I desperately need all of my collaborators, or I would not be able to get this done. In particular, my two advisors, Scott and VJ, robotics and computer architecture, who've really helped me get a lot of this done. And so with that, I hope that today you felt like you learned a little bit about the language of robotics and potentially computer architecture. I hope you think they're exciting, because I do, and I'd love to do some work on that with you. I hope you understand the importance of parallelism, and you'll start to think parallel as you work on algorithms in the future. And I hope you feel like you kind of understand the hardware acceleration flow, and you think it's exciting and cool. If you have any feedback for me, I put together a little feedback link. It's just a little bit.ly thing. It's like a 5-question Google survey. What you think? How's the pace? That kind of thing. I would love any of your feedback. I'm always looking to improve things. You can drop me a line if you want to email about something, and if you want to dig into my research or whatnot, all of my papers should be available on my website as well. So that's sort of all I had, and I wanted to, yeah, we got a little extra time. I wanted to leave a little extra time for questions. So I'll turn it over to all of you.
Great. Thank you so much, Chris. All right.
The base